Profesor Gawem Jenkin es profesor en la Universidad de Leicester del Departamento de Geología en el Reino Unido. Su tema es una innovación metalúrgica en la disolución por líquidos de diversos metales, líquidos orgánicos, según tengo entendido. El profesor Jenkins, shall I speak English? Es un profesor en recursos minerales de la Universidad de Leicester, tiene más de 30 años de experiencia como un geoquímico y mineralogista, con un énfasis en exploración mineral y génesis de minerales, en particular oro, y ha publicado más de 50 documentos. Los proyectos más recientes incluyen el depósito de Cononish en Escocia, en Chipre, y el BMS, y un reenfoque de la mineralización de Broken Hill. Recientemente, él ha liderado una colaboración grande importante con el profesor Andy Abbott en química y en Leicester para desarrollar la aplicación de líquidos iónicos solventes para eutéticos agudos o profundos para el procesamiento de minerales. Trabajando en conjunto con compañías mineras en Reino Unido, Suecia, Perú y las Filipinas. Es investigador coprincipal de un proyecto actual de 3.300.000 libras esterlinas del consorcio NERC-SOS sobre reciclado y suministro de telurio y selenio. Liderando el paquete de trabajo de una aplicación de solventes de eutético profundo a una recuperación de subproductos. También es co-investigador en la red europea de entrenamiento Sócrates para el procesamiento sostenible de metales, desechos conteniendo metales críticos y también de desechos que no tienen valor. Ha sido director del grupo de estudios de minerales del 2010 al 2013. Él es miembro de la Sociedad Mineralógica y profesor en grado 1 del Instituto de Materiales, Minerales y Minería. Presentamos acá al doctor. Please, you are ready to directly lecture.
Okay. Thank you very much. This is the University of Leicester. I just want to introduce you to it. Often mispronounced. You may know about Leicester because of the wonderful victory of our football team, very surprising last year. They're back to normal now. But Leicester, the university, is also the home of DNA fingerprinting. It was where it was invented, and it's now used worldwide to solve all sorts of forensic cases. And also recently we discovered the remains of King Richard III, the last king in England to die in battle. Okay, so what are the drivers of the mine of the future that we need to be thinking about? Well, the main thing really is this, the decrease in ore grades. Now, partly this has happened, you can see here for gold, this has happened because we develop processes that allow us to mine large bulk tonnage deposits at low grade, but also it's happened because we've actually mined out the high grade, easy to find deposits at the surface. So the grades are going down and down, and you can see the grades of discoveries are always underneath that, pulling that further down. Okay, so we are going to continue that trajectory downwards. Okay, and also more recently, as I said, we found all the obvious easy to process deposits, and people are now going back and looking at the ones that are more difficult to deal with metallurgically. So high arsenic, energite bearing ores, we're looking at those as well. And both for the low ore grades and for those difficult to process ores, we're having to put in more energy per unit metal to get that metal out. Okay, more and more energy, not a good thing in the present climate. Okay, it's a greater cost and a greater environmental impact. Okay, so the mine of the future needs to worry about climate change and stop producing carbon dioxide. We need to worry about more extreme weather, whether it's floods and hurricanes, as we see now in the Caribbean, or water scarcity in Chile, where increasingly, mines are in conflict with other users of the water for that. And I heard yesterday that in Peru, 70% of conflicts related to mining relate to water usage. Okay, so we need to reduce our water usage. We have a public that is increasingly aware of what happens in mines and increasingly intolerant of bad behavior. So we have to work harder and harder to be more environmentally friendly. And the mine of the future needs to not only use carbon-free energy sources to power it, such as solar panels, but it also needs to find the materials to power a new green energy future. We need to find the rare earths, and we need to find elements such as tellurium, which we need for solar panels. And we actually run a big project where we're looking at finding more sources of tellurium. Okay, and in terms of environmental impacts, then obviously artisanal mining is a big issue. And the use of mercury is something that we really need to worry about. So a huge quantity per year is used in artisanal and small-scale mining, but we have to acknowledge that it's a significant proportion of the world's gold supply, and it provides income for 10 to 15 million miners and their families in areas of high poverty. So we can't just ask artisanal miners to stop. We need to provide them environmentally friendly replacements for the use of mercury. Okay, now this is very simplistic, but this is what we think about traditional ore processing. In simple terms, we take our ore, to get the metal out, we add energy. Okay, that energy costs money. And the end result is we produce our metal, but we have a CO2 footprint from the energy input, which we don't want, and we also produce wastes, okay? Solid, liquid, and gaseous waste that we need to deal with, and those are expensive, and those have a associated carbon dioxide footprint. Okay, now it has to be said that some of the reagents used are not popular with the public. Now, I have to say, I completely understand that cyanide, when properly used, is absolutely no problem. Unfortunately, the public relations has been completely lost with cyanide. Okay, and so in many countries it's now banned, and there's increasing public pressure to stop using it. Okay, so what, just for purposes of illustrations, if we look at gold mining, 3,000 tons of gold annually, we've got a CO2 footprint from that. We can calculate of around 35 million tons of carbon dioxide that goes into the atmosphere, contributing to climate change. Compare that with copper mining, 57 million tons, okay? And this is really they're reflecting the fact that we're working always with very low grades in gold. And that gold mining might consume 2,000 gigaliters of water. That is 2 cubic kilometers. That's a vast amount of water. And 0.4 million tons of cyanide. So what we need to do going forward is develop additional low energy, low cost processes that are environmentally compatible and recover byproducts. Now, obviously, there are lots of low energy processes, heat leaching, bioleaching, etc., but they don't necessarily recover the byproduct elements that we might want to be getting out, like tellurium. So heat leaching for copper will leave tellurium behind. Okay, so we think one way forward, and it's not the complete solution, but is our ionic liquids. This is a potential disruptive technology that could completely change the way we operate in parts of the industry. What are ionic liquids? They are anhydrous salts, okay, that are liquid at low temperature, usually at room temperature. Okay, so when you look at these liquids, you have to get out of your head the idea there's any water in them. They are water-free, okay? Once you take water out of the system, you change chemistry completely. Humans are used to aqueous geochemistry. It's what we grow up in and experience, okay? And in aqueous systems, the water is always trying to precipitate the metal as an oxide or a hydroxide. You take away the water, that effect completely disappears. Okay, so if we look at the table here, it compares the concentration of chlorine and chloride and water in different substances. Okay, so water, as you might expect, has a high concentration of water in it. Okay, but if we look at our ionic liquid, in this case ethylene, we have a high chlorinity and 0 water. Okay, but the chlorinity here is similar to what we'd have in 16% hydrochloric acid. That's pretty strong. But that hydrochloric acid would still be mostly water. And even if we go to the most concentrated hydrochloric acid that you can get to, it is still mostly water. Okay, so we're going to get rid of water, change chemistry. Okay, and these liquids are ionic, and therefore we can do electrochemistry. Okay, and they have a wide potential window, so wider than in aqueous systems. Okay, so our chemists in Leicester have developed these, and they've successfully been using them to recover metals from high-end scrap, things like rhenium from turbine blades, and from various metal oxides. And the idea is that we recycle our liquid, and you don't end up with large volumes of low concentration aqueous waste that needs expensive treatment. Now, if we're going to apply this on a very large industrial scale at a mine, then we need something that is available in very large quantities. Obviously, it needs to be cheap, and it needs to be environmentally compatible. Now, if you Google ionic liquids, it's not a new field. They've been around for decades. But the vast majority of them are either very expensive or toxic, and therefore not appropriate for a large-scale industrial use. Okay, but the real breakthrough here is what our chemists discovered at Leicester, where they developed a new class of ionic liquids called deep eutectic solvents. Okay, and this is a mixture of an organic salt, choline chloride, and a hydrogen bond donor. So common chemicals such as citric acid, such as ethylene glycol, such as urea. And we mix the two together, and they may have high melting points themselves for the two things. This is the urea, but when you mix the two together, you form a eutectic mixture that is liquid at room temperature. Okay, so we have patented over 1 million combinations of possible liquids, and that allows us potentially to adjust the solvent and its properties for particular applications. Okay, so this eutectic, we take two solids and make a liquid. And if you don't believe me, I'm going to show you. Solid 1, solid 2. You mix them together, and you get a liquid. That's magic. Okay, so what are these chemicals that we are using? Our choline chloride. It's vitamin B4. Okay, no one can argue that is toxic. And it is produced around the world on millions of tons scale because it is used as an additive in animal feed to sustain the animals. So therefore, it is cheap and easily available and clearly non-toxic, biodegradable. Another component, for example, urea. Well, everybody in the room is making urea. Okay, clearly it's non-toxic. And it's common fertilizer, again, produced in factories worldwide, very cheap component, biodegradable. Now, people often say, well, what is the comparison in price with cyanide? It's not possible to do a direct comparison because this is what you pay approximately for buying cyanide, but obviously that cyanide is diluted very much to be used to leach gold. So it's used in a different way, and you might have an extra cost for removing that cyanide or recycling that cyanide, whatever you do. Whereas in our systems, we have a cost, but the idea is you recycle your liquid many times. Okay, so this shows the sort of selectivity we have as a result of the various flexibility in what we can do. So what we're trying to do here is we're trying to recover the metal blue. And we have two modes of dissolving our mineral. We can make our mineral an electrode and add or subtract electrons and cause it to go into solution. Alternatively, we can use a chemical oxidizing agent, and we use dominantly iodine, which is very environmentally benign and safe. Okay, so we can oxidize it into solution. Once it's in solution, we have various modes for recovering it. We can electroplate it out. We can co-precipitate it with something else. We can put in a more reactive metal and cement, or we can use ion exchange. Or alternatively, there is a fifth option where we can actually add water because our ionic liquids are completely miscible with water. We can add water and make it become an aqueous system, and then those metals that are not soluble in an aqueous system precipitate out. Okay, so let's show you an example. Gold dissolution, so I'm going to have to hurry up. Here's an example of a polished block. And what we're going to do is literally dunk it in our ionic liquid. And there you can see that the electrum, the gold-silver alloy, has dissolved. Okay, now you say, why does gold dissolve? It's it's very hard to oxidize, but that's an aqueous system. So here we've got the redox potential in aqueous systems for various couples compared to in our ionic liquid, and you can see that gold is over here. It has a much lower redox potential in our ionic liquid, so it's much more easy to oxidize. So anything below the one-to-one line here is actually easier to process and oxidize. Now this is just one ionic liquid. If you change the ionic liquid, you can change that pattern. Okay, here's an example of taking your gold, putting it into an iodine solution in our ionic liquid, and then recovering it on the electrode. And we can see that the material deposited on the electrode here, if we look at the filled triangles, is generally more gold-rich than the starting composition shown in the circles. Okay, so we can potentially, by adjusting the voltage, recover the gold separately from the silver. Okay, now you might be thinking, well, are we not going to use up lots of iodine here? Well, no, because we can recycle it very easily at the anode. So we form iodide that is recycled to iodine and then reused again. So the iodine is used as an electrocatalyst here, and it essentially allows us to contact the anode with the mineral. And then the metal, or one of the metals, is plated out. Okay, the picture you saw before was done on an optical profiling microscope, and that allows us to measure the height of the surface very precisely. So what you can see here is those same images in 3D. I'm not sure this is right. Yeah? It's telling me I've got 12 minutes left. Okay, so we can see here a pit now where the gold has dissolved away. And our microscope is measuring that surface very precisely. Okay, so we can subtract one from the other and measure the depth of that pit, 1.7 microns. And this allows us to measure the rate of dissolution. Okay, here's another example. So we have pyrite and electrum filling a fracture. After 5 minutes, the electrum has dissolved away. If we look here in a plan view, we take a profile across the surface before and after, and we compare the two, and we can then subtract one profile from the other. Note the initial profile, there's a depression where the gold is because of the polishing. We subtract one from the other, and we can work out how much gold, what depth of gold has dissolved in 5 minutes. Okay, so this is the data set that we had about 2 years ago now, where we had the leaching rate of various minerals, time against amount dissolved. So increasing slope here shows a faster rate of dissolution. Okay, now remember our pyrite doesn't dissolve at all. Neither do your gangue minerals, silicates, most oxides, carbonates, and what we have here are our sort of sulfide and telluride minerals. So starting at the bottom here, we have chalcopyrite, that hardly does anything, but bismuth telluride, we have galena, tellurium, that one's altiite, lead telluride, and then in orange here we have electrum, and here we have in red hessite, silver telluride. Okay, so at the bottom, in dashed blue here, we have the cyanidation rate of gold at 25 degrees C. Now, obviously, our data are at 50 degrees C. It's not a direct comparison. Our rates would be slower at 25 degrees C, but our rates are much, much faster here. Okay, so we can easily dissolve gold as electrum, but we can also dissolve hessite. So if you had a deposit which had both of those in, and in fact the samples actually came from our little gold deposit in Scotland, Conninish, then that contains a considerable amount of tellurium as hessite, and we'd like to be able to recover that too. So we should be able to leach out both the gold and the silver and the tellurium and recover those. Okay, now if we just look at the rates and look at the quantification of them, if we just look at this point here, so the lowest rate measured for the electrum, and there is quite a variation here, so I can explain that later on perhaps in questions. But if we take that point, 10 minutes, we've dissolved 4 microns. Okay, let's just do some very simple calculations. If it dissolves 4 microns in 10 minutes, then even if we have a big grain, 100 microns diameter, then that would dissolve in less than 2 hours. Okay, and if we use the fastest rate, 1 hour. Okay, so that leaching rate is about 80 times faster than the cyanidation rate. Okay, so what we've got here, just looking at gold, is a potential alternative to cyanidation, smelting, or mercury. Okay, so potentially much better process. Okay, so we've got these data on how fast material dissolves on the surface of a section, and we're using this to model bulk leach experiments that we're now running. Okay, so here we've got an example of a heavy mineral concentrate from the Rhine River in Germany, which contains gold. And we can see in reflected light we have a number of gold grains. But in most sections of this material, you might get 2 or 3 grains. So you're not getting a very representative sample. So what we've done is take our sample and put it in a micro CT X-ray scanner and look at it in 3 dimensions. And this allows us to pick out all the gold grains and look at their size and shape. Okay, at the back. Okay, here we go. Okay, so we can pick out the gold grains, we can see exactly how big they are, and we can measure those very precisely. Okay, so we gain data not on a few grains, but 233 grains. We can look at the grain size distribution. It's pretty coarse stuff here, dominantly 70 microns, but up to 200 microns. We can take that grain size and we can convert it to a weight, and we can see that our dominant weight size class is 100 microns. But interestingly, you know, the big grains, there's only 3 of them here, but they contribute about 10% of the gold. It's always important to look after your nuggets. Okay, we can add all that up and we can actually measure or give an estimate of the total amount of gold in the sample, okay, which in this case is around 330 grams per ton. Okay, and then we can model how these grains are going to dissolve. So if we look at the left-hand axis, this is our largest grain at a linear rate of 4 microns in 10 minutes, or it will dissolve in this way, and that's our smallest grain. The volume obviously is related to the cube of the radius, so it actually goes down much faster here if you look at the right-hand axis. We can do that for individual grains and then add them all up in a spreadsheet, and we come out with a what we think is going to be the bulk leaching behavior of the whole sample. Okay, this is our prediction, and we can see that in an hour we've got about 75% out, in 2 hours we've got 95%, and then 3 hours we've got 99.5% of the gold out. Okay, this is our prediction. We're now working to do the bulk leaching experiments to test this. Okay, so byproducts, I said, you know, these are quite important. So most mineral deposits, copper deposits, gold deposits, will often be enriched in various other elements. And they may be elements such as bismuth and antimony, bismuth and antimony, which have the potential of supply risk because they dominantly come from China. And if we could economically extract them, then they can potentially add value to your deposit. And we think we can do that with our technique. Okay, but you know, recovering byproducts, we should do it for the planet, okay, because we go to all this effort of finding a mineral deposit, digging it up, crushing it up, and then we throw a lot of stuff away. We maybe get the gold or copper out. But for the planet, we should try and get everything out that we possibly can. But a lot of things are against us. So we look at tellurium, okay, it's gold is worth 400 times more than tellurium. So to get a miner interested in recovering tellurium is very difficult. So what happens typically at the moment, we have our mine, we have our product, which may be gold or copper or both, We have various byproduct elements that are in there. We go through a beneficiation plant, but what happens to the byproduct? It may go direct to waste and not even go any further, or it may go into the concentrate. That concentrate may be processed on site, or often sent off to a refiner, sent off to a smelter. So if it goes to a smelter, that smelter will recover the product. It may even recover the byproduct, but they won't give you any money for that. Okay, the only money that comes back to the producer is for the product. Okay, but sometimes even at the refiner, the byproduct goes to the waste. Okay, and smelters might even have elements such as bismuth as a penalty element, and it actually costs you money. Okay, so the current setup means there's no incentive for miners to worry about these byproducts and perhaps optimize their recovery in their beneficiation system. Okay, now most of these byproduct elements occur in rare, unusual minerals in your ores. Okay, so minerals that you probably haven't heard of most of these. Okay, valinskite, for example. But we've taken all of these, we've looked at how rapidly they leach, and compared them to gold here and electrum here. And this is the cyanidation rate at the bottom. And you can see that all of these minerals are leaching, and they're all leaching faster than cyanidation, so they're all potentially recoverable. But particularly over on the right, a lot of the bismuth and tellurium minerals are leaching as fast, if not faster than gold, whereas in the middle we have a lot of the antimony minerals, which we might also want to recover. Okay, so potentially we can recover these byproducts as well. Okay, so just one example here. We have arsenopyrite, and we have gold, we have native bismuth, we have hedleyite, which is a bismuth telluride, maldanite, a gold bismuthide. The arsenopyrite will not dissolve, but all of those other minerals will dissolve. So potentially from this ore we can recover gold, bismuth, and tellurium. Okay, so we can change that situation and maybe incentivize the producer to put the byproduct in their concentrate, recover it by ionometallurgy using ionic liquids, and you regain money for both the byproduct and the product. So they become incentivized to worry about it. Okay, and you can potentially also do this locally, so you have chain of custody and can market ethical products. Okay, so all I've talked about so far is using iodine as an oxidizing agent. Okay, but a lot of minerals don't dissolve. Okay, most notably pyrite doesn't dissolve, but also our iron arsenic sulfides, lollingite, arsenopyrite. And I guess you can see the similarity of these minerals. It's down to the structure. They have disulfide or diarsenide bonds. They don't dissolve. Now, pyrite, in many cases, we wouldn't want to dissolve. We just want to leave it because it is gangue. But we'd certainly want to recover the calaverite, the gold, and the tellurium, and the platinum minerals here. And calaverite is a big issue because it doesn't cyanide and often is a cause of gold going to waste because it is not leached by cyanide. You can roast it, but then your tellurium, you have to deal with that, and it's an environmental issue. Okay, now we'd like to recover both the gold and the tellurium. And of course, sometimes gold occurs in very fine inclusions in pyrite, sometimes even dissolved in pyrite, and then of course you need to break down the pyrite structure to liberate the gold. This is ore from Scotland, Canninish, and they have electrum in pyrite, and about 25% of that gold they can recover directly, and they sell that as Scottish gold. And they, the first sale of that gold, they sold that as $1,000 an ounce because they could market it as being Scottish. Okay, so big markup for local ethical sourcing. But the rest of their gold is going to go off to a smelter abroad, and it will no longer be Scottish gold. So for them, it may make a really big difference. What we'd like to do is recover that gold on site, okay? And they won't be recovering the tellurium either. Okay, but that brings me to the second mode of dissolution, electrochemical dissolution. Okay, and so we make the mineral an electrode, we add or subtract electrons, and we can cause it to dissolve. So calaverite that didn't dissolve in iodine, okay, you can see it before and after it is dissolving. Okay, so we can deal with calaverite. And we can deal with all these refractory iron sulfide minerals. So here's our starting solution. We make our mineral electrode. We suck out the electrons to oxidize it. And all these minerals, pyrite, arsenopyrite, lolongite, all these copper minerals can dissolve electrolytically. Okay, 5 minutes, that's good, I can do that. Okay, so, and pyrite, interestingly, can dissolve both by oxidation and reduction, giving us great flexibility in the way that we actually deal with it. Okay, so for our little mine in Scotland, this could make a really big difference. We could use electrolytic dissolution to dissolve the pyrite, liberate the gold, and gain a Scottish hallmark for all of that gold. It can be guaranteed Scottish, ethically produced, and gain a high markup. But alongside with that, we can recover byproducts, silver, tellurium, etc. Okay, and it has to be said that ethical sourcing is a real growing market. All those tourists that come to Cusco, they'd love to buy Peruvian gold. Okay, so if you can prove that it's your own gold, and potentially gold that hasn't been produced by cyanide, then potentially you have a market edge. Okay, 5 minutes, literally, I'm going to finish. Copper smelting. Okay, about 80% of copper produced around the world is produced through a smelter, a very high energy, high cost process. Okay, now what we've shown is we can put our mineral, our powdered mineral, against an anode in an electrolytic cell, separated by a permeable membrane from the cathode. We turn that on, and at the anode, the mineral is oxidized, and at the cathode, the metal ions are reduced. Okay, so for example, we can put into here galena, put galena in here, and on the cathode, we plate out lead metal. Now, this is what you do in a smelter, okay? And smelting lead is a huge source of environmental contamination, but we can do it here at room temperature. And similarly, we can do the same thing for copper minerals, so we can go direct from the mineral to copper metal. Now, clearly, this is extremely small scale, and there's a bit of a way to go to replace a smelter, but the potential is there. Okay, and obviously we're working to scale up our processes. We have 6 pilot plants that go up to about a half-ton scale, and we're using those to do our bulk testing in. Okay, so just to conclude, we have materials that are environmentally friendly and hopefully therefore publicly acceptable. We have low-cost materials that are therefore potentially useful at a large scale, a low temperature, low energy process. We have low water usage because we can recycle our liquids, and therefore we're going to produce a low amount of aqueous waste, which is always hard to deal with. We can potentially recover our byproducts as well, maybe adding value, but at least doing a good thing for the planet. Our best thing to work on at the moment would be high-grade complex ores and concentrates, okay? And we can potentially do this locally, on-site, or in country, promoting ethical sourcing. And we can scale it up to large operations and potentially down to small artisanal and small-scale mining as well. So it just remains for me to thank Poderosa for sponsoring me to come over, and thank you for your attention. Thank you very much.
Dr. Jenkins. I want to congratulate you and congratulate ourselves for having been exposed to such potential technology. Please come this way. Ahora vamos a tener una estación de preguntas que ya han sido, van a ser por escrito, pueden ser en inglés o en castellano. Le estaba diciendo al profesor, preguntándole en cuánto tiempo estaría disponible esta tecnología para uso industrial, y estábamos quedando en que podría ser en 5 años, aunque no está muy seguro, ¿no? Por lo tanto, esto hay que verla con seriedad. I wanted to comment something about the lysine. Maybe you know there is another protein. In addition to the choline, there's another protein called lysine.
Yes.
Would you like to comment on the difference? Maybe you know about this.
Yeah, I don't know too much about the lysine approach, but I think it's more similar to using cyanide. So it will be leaching used in very low concentrations. So it's actually quite different from what we're doing, whereas we're using very high concentration liquids, but enabling us to have a lot of power to extract the metal. So, you know, we have to be pragmatic about it. In different places, different approaches are going to be suitable, and we need to find where maybe lysine would work and maybe ionic liquids will work.
Here we have a question. The questions from Edgar Taya Osorio. I'm going to read the question in Spanish because it's written in Spanish. Okay. ¿Cómo influye la génesis, óxidos y sulfuros en la utilización de los líquidos iónicos? The genesis.
The first bit.
How does the genesis or the mineral genesis influences? In other words, the way the minerals are put together in the mineral.
Okay, so obviously it is mineralogy is key, you know, and metallurgists should never forget mineralogy, because it is the most important thing. And our process is very mineral specific, so it will dissolve one mineral and leave another mineral behind, or it will dissolve one mineral very rapidly and another mineral very, very slowly. Okay, but it won't work on oxidized ores.
Okay. There is another question. ¿Cómo recuperar el oro de 3.9 gramos por tonelada con 1.7% de arsénico en un intrusivo diurítico terciario de origen hidrotermal? This is a diuretic intrusive with this amount of gold, with this percentage of arsenic.
Yep. I see no problem why we shouldn't be able to do that, but like I said, it depends on the very specific mineralogy of your ore samples and your concentrates. So each one, you know, each concentrate is different, and we need to assess the mineralogy of that to know what we can do.
Una tercera pregunta. ¿Es necesario considerar algún mineral que funcione como par galvánico para mantener o garantizar la disolución de Samuel Canchaya. In other words, there is a need for some other material for the reaction to work. I understand that you put artificial electrodes. Not really.
Normally, no. No, so normally we will either be able to dissolve a mineral or not. There's nothing else we can add to help the reaction, apart from these electrocatalysts that we use. So we use iodine mostly, but we have other electrocatalysts that we can use, and there's a whole range of those as well. So we have a lot of flexibility, but we need to know the mineralogy of your samples.
This is an interesting one. Para el uso de los líquidos iónicos, ¿se requiere alguna certificación o permiso? De César Eduardo Vargas, Ticona.
Well, we don't think so. You tell me. Would you need a permit for vitamin B4 and for urea? I don't think so.
Bueno, no habiendo más preguntas, despedimos al Dr. Jenkins con un fuerte aplauso. Thank you very much. Thank you. We're going to take a picture.